Thank you for this wonderful introduction. Good morning, everyone. My name is Solomon Wante, as she's rightly said. I'm here to present some of our findings from the 6-month pilot study using Trichoderma to see how we can harness, how we can manipulate the soil microbiome to help us, help vine to tolerate drought stress. So, yeah, I know Daryl and Jim, they have set a quite high standard, so please, I apologize so that if I didn't deliver quite well the way they delivered, so yeah, thank you. I'll start by saying, imagine a future where you have vineyards across New Zealand increasingly threatened by drought. And what is more fascinating, or what is more surprising is data from NEWA indicated that drought index in 2020 is mostly around the northern island, while in 2023 it was quite opposite. But in 2024 we have a very different frequency and pattern of drought stress index, which is mostly around Blenheim and Maltonborough. So that tells us that drought, which is driven by climate change, is hard to predict. It's something that we cannot say where it will happen and how it will happen. So in looking at that, and we know that a situation like this, where you have drought stress and the vines did not receive irrigation, this is one of the effects from having a vine without receiving irrigation. So what we want to highlight here is that when you have a matured vineyard and young vineyards, the way they receive water in terms of irrigation is different. When you have a matured vineyard, you are expected to use 15,000 liters of water per planted hectare per day. But when you have a young vineyard, it will require more. So, looking at future, if we have a couple of days during the summer and we have more dry days than we ever experience, are we continue to irrigate more, or are we going to cut down some of the vineyard we have? So what we are looking here to explore is that we have the opportunity to harness the potential below ground. We have microbiomes that are there that can help us to eliminate this drought stress in vine. So one of the beneficial mechanisms that microorganisms use to tolerate drought is by water retention. So microbes, especially bacteria, they can secrete some extracellular enzymes, and these extracellular enzymes, they can plug into different soil pores. By doing that, they can retain the water, and plant root can be able to harness this water when it needed during drought stress. It uses different mechanisms. Some of the fungi, we have them in the soil, they can be able to produce some hormones, and these hormones can increase root biomass, and when you have root area or root biomass, it can help to maintain water retention in that root zones. So we are looking at using Trichoderma. The idea of using Trichoderma is that we know that we have some Trichoderma that are originally in the soil, but what we want to do here using Trichoderma is that when you have a young vine, our interest is on the young vine. When you have a young vine, and you put it in the soil, the young vine has no mechanisms to select partnership with the microorganisms. But we want to use Trichoderma because this Trichoderma has been validated by research for so many years, even within the industry, that this Trichoderma has some biocontrol against some certain soil pathogens. So when we have this Trichoderma in soil, it can serve as parent to these young vines by selecting the microbes that are that they can form beneficial relationship. Just like when you have kids, you have to be there for the kid to tell him, don't take this, you don't need to drink this at this time, and you guide him. This is how this trichoderma will work. That is one of the mechanisms. But another mechanism that trichoderma use is that trichoderma can, one of the, trichoderma has high tolerance level to heat. Trichoderma, you can grow trichoderma in vitro at around 45 degrees, which is quite unique compared to other fungi. But when you have trichoderma in the soil, trichoderma can be able to secrete some enzymes to inhibit the growth of other microorganisms, whereby providing a root zones that are basically healthy for the further development of the roots. Therefore, I have highlighted these different mechanisms whereby trichoderma used as biocontrol. 4 of them is basically biocontrol, but the other one is inducing systematic resistance. The systematic resistance is that trichoderma can be able to secrete a certain type of auxin, and this auxin can regulate the opening and the closing of stomata. So when plant undergo drought stress condition, with the help of trichoderma, because trichoderma can travel from the root up to the stem of the plant, and it can be able to regulate the gut cells around the stomata, so that the gut cell can send a signal that we need to shut down, or we need to optimize the way we can be able to release oxygen and absorb carbon dioxide, so that we can make optimal photosynthesis. By such doing, trichoderma has that capability to help young vines to establish quickly, and when irrigation resumes, it can be able to flourish well. So we designed this potted experiment, and we use 2 different soil types across Marlborough area. And these soil types are different in terms of their physics, chemistry. So, but one of the important things here is that this soil type, where our soil type has high salinity content, while other has not. So we want to see how trichoderma will behave in this different soil type. So we collected soil from bog soil, and after collecting the bog soil, we used 12 liters of parts. And the way we collected this soil in different soil horizon, the 0 to 10 centimeter, 10 to 20, then 20 to 30. And we simulated the same pattern of horizon into the soil, in making sure that we are mimicking how this soil is in the natural environment. What we are trying to do, because this is the pilot study, we want to see how closely we can mimic natural environment into the glasshouse setting in order to monitor, in order to ask some few basic questions regarding how we can harness the potential of this trichoderma. So one of the technology we are using at Brigato Research Institute is the use of sequencing technology. The nanopore sequencing technology has helped us to visualize what community memberships are in this soil, so that we can be able to establish at the baseline that this soil type that we are using, the Fairhole and the Wairau soil, what are the community composition in terms of microorganisms? Because we are going to inoculate this soil with trichoderma, so we want to know how much in abundance we have of this trichoderma in this soil. And after the treatment, we want to see whether this trichoderma has eliminated some microbes or increased the abundance of some microbes. So the nanopore sequencing has quite a helpful tool for us to visualize this. With this now, you can be able to sequence long-read sequencing compared to what we normally used to have before. So in the experimental design, we created some timelines, like baseline 1, and we induce stress for 2 weeks. Then later recover it, standardize a baseline again, recover it, and induce for 2 weeks. From this potted trial, one of our colleagues, she's looking at the epigenetic changes. What changes between when we induce stress tolerance in these young grafted vines? She's looking at the changes within the methylation changes within the gene expression. So one of the interesting things here is that when we look at the warehouse soil has high salinity content. I mean, the EC is quite high. It's about 2.25. I didn't put it there. But for the Fairhold soil, it's about 0.06. But when we look at the cation exchange capacity, which is one parameter that you can be able to use to ascertain how nutritious this soil is, it has high nutritional value compared to Fairhold soil, but it has high salinity content. So it will be interesting to see already that the soil has a stress factor, because salinity content in soil is a stress factor. So it is interesting to see how Trichoderma will behave when you induce drought together with the salinity content. This is multiple stress factor. So we want to as well understand how this Trichoderma will behave in this soil. So this is what we did at the initial stage to create a baseline to check whether within the 10% of the soil microbiome, whether we can be able to detect Trichoderma at the abundance level, relative abundance level within the 10%. So, but in all the soil type, both Fairhold and the Werrao, we did not detect Trichoderma at 10% relative abundance. That is it's not telling us that we don't have Trichoderma in the soil, but we have Trichoderma in less abundance. That is why it's not showing at 10%. We went further again, but the data we didn't show it here, to see at 20% relative abundance, the Trichoderma didn't appear even at 20% relative abundance. So it will be interesting to see after our trial whether we have more Trichoderma in the treated soil with Trichoderma or not. So while we are looking at the Trichoderma effect, we also explore to look at what happened within the stomata conductance, because stomata conductance and photosynthesis, they are fine physiology parameters that will give us an indication whether if we have any sign below ground, what is happening above ground. Is this Trichoderma influences significant changes above ground? And we can use these fine physiology parameters to answer those questions. But here, in the Fairhold soil, there is no significant differences between the stomata conductance in both Fairhold and in Fairhold in both control and drought stress. We went further to see whether there's any changes in photosynthesis rates. In Fairhold, we see some differential changes. One of the interesting ones is when we stress vines under the first stress, the first stress point, we can be able to see, like, with Trichoderma, it improves photosynthesis rate quite well, but we don't know. But in the second phase of the stress, it goes down. So this kind of differential treatment, we are not quite convinced that we have optimized it yet, or the Trichoderma is pushing the effect on the above ground, but we want to really connect the two. What happened below ground and what happened above ground, and what changes within the soil space in terms of microbiome diversity. So going forward, to compare it with Werrao soil, in Werrao soil, we have similar situation in terms of, we have a different situation in terms of stomata conductance. Here, when we recover after inducing stress for 2 weeks and recover it, we see a consistent change in stomata conductance, meaning improvement in stomata conductance. But we need to see whether this stomata conductance will influence a good photosynthesis rate. So here, we can only see that stomata conductance has influenced photosynthesis rate in only recovery 1, but in recovery 2, there is no significant differences. So therefore, we conclude that Therefore, we conclude that the above gram using the fine physiology, stomata conductance, and photosynthesis rate. At this first year, we did not observe a big significant difference within the stomata conductance and photosynthesis rate. So we went further to see the below gram. What happened below gram when you have this trichoderma? Interestingly, in Fairhall soil, and this is the control soil, addition of trichoderma has significantly increased the root biomass and even the root morphology. Taking cognizant of we are using only 12 liter pots, that may hinder the deeper growth of this root. But we are aware that that will happen. But even at that, we can see we have significant increase in root biomass and root morphology in the control treatment, meaning we did not induce stress at this level. So when we look at this one, where we have induced stress, there is no significant difference between the one with trichoderma and the one without trichoderma, but what we found that is more significant here is the root morphology. Obviously, you can see the lateral root it has occupied a big surface area, meaning it can give a good water retention, but we are yet to conclude that yet. So when we look at the viral soil, in the control one, the only thing we see that is more significant here is the root morphology, not the root biomass. But the interesting aspect of this here in the viral soil, remember this soil has high salinity content, and we induce stress in this soil. So what we saw here is quite interesting because trichoderma induce root biomass and at the same time root morphology. Therefore, we say, okay, let's look at what changes within the soil microbiome space in terms of, so we created two pipelines, one for bacteria and the other one for fungi, meaning we want to see the abundance of bacteria and the abundance of fungi in this soil as with under control and drought stress. So diversity within the bacteria in water stress, we see a low abundance, we see a reduction in diversity of bacteria when we didn't treat it under drought, but when we induce drought stress, it still shows in the soil treated with trichoderma has low abundance of bacteria. And in viral soil, in the control one, we see the abundance of bacteria has been reduced in soil that has trichoderma, but there's no significant differences under drought condition. In Fairhall soil, we see the relative, this is for the bacteria, we see significant differences in both the water and the control. Here this is the viral one, and this is the drought. And the drought, remember the root biomass from the drought treated with trichoderma, we witness improved root biomass together with improve in root morphology. And here we have increase in fungal population. And when we treated it with under drought condition. So in summary, trichoderma did not appear in the 10% core fungal genera across the baseline soil type. Trichoderma did not cause significant changes in stomata conductance and photosynthesis rate. In first year, trichoderma reduced the bacteria population while increasing the fungal population in soil type, a process known as soil microbial antagonism or competition. This led to improved root biomass and morphology under both drought condition, under both control condition and drought stress condition. Yeah, I want to thank these people, Daryl Limazor and my colleagues for helping out in this project, and Hussein from Lincoln University, and Stewart from NMIT. Thank you so much.